Today we will study electrochemistry. Electrochemistry is basically where the where let's say the particles, elements, molecules, the compounds, these are actually made to pass electricity, or these are used in order to complete a circuit by making a contact with the power supply. For example, let's say this is the sodium chloride solution, and we have, let's say, placed two wires, one of negative terminal and the positive terminal, and both the ends are connected to, let's say, the positive and negative terminals of a cell or battery. Since this is solution, that means ions are free to move. And since this is a sodium chloride solution, so it was ionic, forms an ionic solution. Hence, the ions are free to move and conduct electricity as per required. So that's basically the electrochemistry's main concept, and which we will be studying in this topic. Uh, so over here, from this diagram, what we can observe that there is a this system, or this substance, or this portion of the substance, which actually is not a metal ware. This is a solution. This could be a solution. This could be liquid. This could also be solid. But we will deal this with solid. But most of the time, we will be dealing with liquid and solution. Solid could be, like, an example of solid could be, let's say, pure copper or iron, like, which are metals, which helps to conduct electricity. But other ionic substances, they don't conduct electricity in their solid state, because there is no free ions to move in ionic compound in solid state, or yeah, like in solid state. But mostly we will deal with a solution or liquid substances, because in liquid, the particle, like the compound, is free to move, like the ions are free to move, and, like, let's say, for example, sodium and chloride, then they will be dissolved, like, sorry, they will be, if they are solid, now when they are converted into a liquid, what happens? The ions are free to move. As well, when they are, like, dissolved in water, they are also free to move, with the specialty that there is now hydrogen and hydroxide ion. So that actually helps them to form the ions. Now, about this portion, which is this liquid or solution, this is known as the electrolyte. Electrolyte. Electrolytes are what? Which helps to produce ions in maybe the molten state, as I've said, or in solution, and conduct the electricity. So if these are electrolytes, then what will be those which does not conduct electricity? Those are non-electrolytes, since they cannot conduct electricity or cannot form ions in their solution or molten state. Those could be the covalent compounds. Good examples of electrolyte could be sulfuric acid, H2SO4. Then it could be NaCl. It could be CaSO4. All should be, like, I'm mentioning them in terms of, like, their aqua state, like all are solution. Because melting them takes, like, require a very high temperature. So we will generally consider their solution, like soluble states, when they're solution, like when they form solution. And non-electrolytes could be, let's say, sugar solution. The sugar contains glucose. Glucose are, like, you can say, starch. So those are like covalent simple molecular substances which does not form ions. Then we have hexane, methane, ethane, or ethanol. Those are so organic substances. Usually they are, like, non-electrolytes. Not about those who are, like, who forms ions in the aqua state, for example, the acid. So we're not talking about them, rather only those which does not form ions. Okay. So From electrolyte, there are strong electrolytes and weak electrolytes. Strong electrolytes are those which completely ionizes, forming like iron, completely forming more ions, like all of the element, all of the particles therefore like are converted into ions. While weak electrolytes are those which produces less number of free ions in like maybe solution or in the molten state. So strong electrolytes could be NaCl solution, HCl, hydrochloric acid, then H2SO4 or sulfuric acid. Remember one thing, if H2SO4 was given as solid or gas, those we don't consider as acid. Why? Like same goes for HCl. Why? Because in the like what defines an acid? The presence of H plus ion, isn't it? So in solid, there is no presence of H plus ion. Like it cannot, it is not free to move. If H plus is not free to move, then it does not act as an acid. So that's why in aqua, like we did solution, like aqua state to say that as acid. Now, the formal definition of electrolysis, this process itself is known as the electrolysis process. And electrochemistry is basically dealing with the like electrical parts in this system, like making electricity to work and make like and analyze the components. So electrolysis, this process which we just do, is known as the electrolysis. And the formal definition of electrolysis is it is a process which in which like electrolytes are decomposed by electricity in the molten state or in solution and made to participate in the conduction of electricity. So that is our formal definition of electrolysis. Let's move forward. Now in this electrolysis, we draw the beaker again. Now usually, like oftentimes we actually place these two rods into the like solution. We dip, we submerge these two rods in the solution, and on the top of the rod we connect the wires, which in like or it further connects to the cell, or if some other connection is required, like it completes the circuit. Now these two rods, these are known as electrodes. These are electrodes. Both of them are known as electrodes. Now why did I say both? Because one of them is like both are not the same electrode. One is known as an anode, another is known as cathode. Now, which one of them is cathode? Now, cathode could be defined with the term cation. Cathode, cation. Like the electrode which attracts cation is known as cathode. So, cation has a charge of what? Positive. So, which charge is going to attract a positive charge? Negative. That means it should be connected to the negative terminal. So, the negative terminal is known as the cathode. Thus, vice versa for the anode. The positive terminal is known as anode because it attracts the anion, the negative charge particle attracted by the positive terminal. Okay, so these are some of the like some of the information. So that means when a positive ion comes in contact with this negative terminal, what happens? A positive ion actually has a deficiency of electron or like less number of electrons, so it will try to gain electron. And gaining of electron is what? Reduction. Reduction is gaining of electron. And for anode, a negative charge particle has greater number of or surplus of electron. That means it tend to lose electron. So loss of electron is what? Oxidation. Oxidation. Since both oxidation and reduction is occurring, that means an in electrolysis process, the reaction that occurs in, like the reaction actually occurs is known as a redox reaction. We know already redox is what? A reaction where both reduction and oxidation take place. Now, let's just do a simple example or show a simple example. let's say we have this cell, and they're connected to electrodes. This is the beaker. The electrodes are submerged into the beaker, into the solution or electrolyte. The electrolyte is, let's say, a PbBr2 liquid. Okay, this is the cathode, and this is the anode. So if we write each of the equation in the like in the each of the electrodes in the cathode, we have what? We will be having the positive ion. Now, which one from these two element from these ions are positive? The metal part, Pb is the metal, which is the positive one. So Pb, and how can we find what is the charge? Now, let's come to bromide. Bromide is a group 7 element who has a charge of what? -1. Since we can see there is like two bromide required, so that means the overall charge is -2. This two we can place it as a like we can consider it as the charge of or like Pb or lead. So that means the charge of lead is Pb2 plus. So Pb2 plus is going to gain two electrons to form Pb. Yeah. And we can also give just a single arrow for like for right now. But usually there's a like two-way process, or like you can say like a two-way direction. So if one like if like equilibrium doesn't like break, like if equilibrium breaks, the other way can also occur. But for simplicity, cathode reaction in one way reaction it occurs. And for the anode part, we have bromide minus electron equals to Br. But we need to form bromine, isn't it? Br2, because Br2 is a diatomic molecule. That means we have to also consider two bromide on the left hand side. That means it is going to lose two electrons. Now don't confuse this minus charge with this minus charge. Electron is just like a negative particle. Let's just forget it. But think, if a negative charge particle is there, and if we need to like reduce the or get rid of that minus charge, what we need to do? We need to get rid of minus charge, and get rid of means what? Subtraction. We're getting rid of. So that is the main concept. And here we have 2 mole of actual electron, isn't it? For like before electron, we can see in the equation we have two, so that means we need for this cathode reaction 2 mole of electron. So 2 mole of E minus. This means actually 2 farad. It's a unit for like measuring charge. So 2 farad means 2 times 1 farad, and 1 farad means what? 1 farad means 96500 coulomb. Now in physics we have most probably read the term coulomb. If like, even if we didn't, it's completely fine. Just know that this is the number of like in 1 farad there is this number of charged particles, coulomb. So same goes for, let's say, if the so like if here instead of PbBr2 liquid, if we had, let's say, solution, uh let's say sodium chloride, NaCl, that moment we will have actually more than two possible ions. Na plus is one ion, Cl minus is the other ion. And for aqueous, like for water, there is H plus and OH minus. So these are the actual like, element, like actual ions present in the solution. Now, as I have mentioned, that if the like if instead of molten state, if there was a solution, then which one of the elements will be like used, or will there like, be participating in the electrolysis? So at least like one of them has to go to the each of the electrodes, isn't it? So for the anode, for the anode part, the anions are going to be discharged, and for the cathode part, cations are going to be discharged. Now, see this chart. This chart will actually help which one is easier to discharge and which one is harder to discharge. The one which is easier to discharge, and that will be going to the electrodes to be discharged. So let's say we have sodium and water, isn't it? Hydrogen, sodium and hydrogen, like sodium chloride. So sodium and hydrogen means sodium is over here, which is towards the harder part, and hydrogen is down over here, like third last. So hydrogen is much more easier to be discharged. So that means hydrogen will be discharged in the cathode. On the other hand, if we come to anode, over here we can see chloride and hydroxide. So from here we can also get to know actually chloride is harder to be ionized, like for harder to be discharged than hydroxide. But here comes one thing which we need to consider. Let me show. So if let's say we are using NaCl, but instead of normal NaCl solution, they mention it is concentrated, concentrated, or they have mentioned aqueous. Okay, concentrated or aqueous. So that means there is actually like 50% concentration or more concentration of chloride ion. Like the negative ion has a portion of 50% compared to the other hydroxide ion. Okay, so if the concentration is greater, that time we have what? More chloride is crowded nearby, isn't it? So no more chloride is crowded nearby the like, anode. That means chloride will be the dominating factor here. So instead of hydroxide in that case, chloride will be discharged. Remember, if they have mentioned concentrated or aqueous, that means actually like aqueous or concentrated. Like aqueous means there is 50% of chloride, and concentrated obviously means like more concentration of like the substance. Now let's do an like do a simple calculation to make things clearer. Let's say we have been given a solution. It's the copper 2 sulfate, CuSO4. Now they are asking us, okay, rather than CuSO4, let's do H2SO4. Yeah, H2SO4. So H2SO4 sulfuric acid aqueous solution. Now they are saying the current being produced is what, 40 ampere. The time for this, like the current being passed through the solution, is for 26 minutes. For 26 minutes, they are passing this amount of current. Now they are asking us to calculate the volume of oxygen produced. So volume of O2 being produced is what we need to find out. At first, let's plot the situation. Let's think about the situation. We have the cell, the electrodes, solution or the electrolyte actually, which is H2SO4 aqueous. And from this H2SO4 aqueous, what are the actual ions present here? H plus, SO4, 2 minus, and OH minus. Now, if we come to the reactivity series, what do we see? Which one is more easier to discharge? Obviously, there is only one type of positive ion, cations, hydrogen. And for the anions part, see, sulfate is far more, like the difference between sulfate and hydroxide is like a lot. So in case I said chloride, if it was concentrated, same goes for bromide and iodide, because the difference between C hydroxide and iodide is very less than bromide and then chloride. For up to chloride, the concentration factor it matters. But if say it was given concentrated sulfuric acid, sulfate is so much like it is so much higher, or the difference is so much high that it doesn't have any effect because sulfate is like it's very hard to like discharge. That's why only hydroxide will be discharged in that situation. But for the exceptions are chloride, bromide, and iodine. Now coming back to the slide, that means from here actually sulfate won't be discharged. H plus and OH minus will be discharged. So H plus will be going to the like going to our negative terminal, and OH minus will be going to our positive terminal. Now let's write the equation, the ionic equation or the electrode equation. For cathode, we have H plus discharging, gaining electron, forming H2. So 2H plus and 2E minus. Then we have for the hydroxide part, OH minus. The actual ionic equation we need to remember that hydroxide when it is discharged, when it actually reduces the electron, it actually forms oxygen and water. So now we have to balance it some way, like how to balance it out. So let's say we have oxygen to the right, and there is one oxygen. So three oxygen to the right, and one oxygen, one hydrogen towards the left. Now how can we balance it? So we can try to actually fix a number by, let's say, we place 3 over here, and we see if it balances or not. But we can see 2 hydrogen is on the right side, so it doesn't balance out. If we write, let's say, 2 over here, so 2 hydrogen, but on the right hand side there are 2 or 3 oxygen instead of 2 oxygen. If that also don't work, let's give 4 to the right. So 4 oxygen and 4 hydrogen. Let's see if it the balance. So we have 2 oxygen over here and 3 oxygen over here. But if you place 2 here, that becomes 4 hydrogen and in total 4 oxygen. That means that works. So we need to actually reduce 4 electrons from the left hand side as well. Now this is one of the equation, and that's another equation. This is the anode equation, that's the cathode equation. Now if we do the calculation, what do we see? We can see actually like they actually at first wanted us to find the volume of oxygen. Now if we use the information over here, we are getting rid of, or we are actually getting rid of 4 electrons, isn't it? Now they are providing us 40 ampere of current for a total of 26 minutes. We can try to find the total amount of charge being like supplied, isn't it? We know Q equals to IT. So Q is the charge, amount of charge. So I into T. Yeah. Consider one, like always remember one thing, we have to consider the time in seconds. So 40 times, we have to convert this minute into seconds, which is 26, and into 60, because 60 means for 1 minute, it's equivalent to 60 seconds, so 26 minutes into 60, that means 26 into 60 seconds. That's our total amount of charge. So if this is the charge, and from here, the equation, we get to see 4 mole of electron, 4 mole of electron produces 1 mole of oxygen, is it? And 1 mole of any gas, like oxygen in this case is gas and water is liquid. 1 mole of any gas at room temperature, we know that is equivalent to 24 dm cube or 24,000 cm cube. So if this is 24 dm cube, and 4 mole of electron means what? 4 farad, which actually means 4 times 96500 coulomb or charge. So if that's the case, and this is the coulomb or charge actually for like which they have been provided us. So now the term is 4 times 96500. From this amount of charge, we get what? 24 dm cube of O2, isn't it? From this charge, we get this much of O2. Then from 1 coulomb of charge, how much we will get? 24 divided by number of charges, because we need to divide for all the charges in order to get for 1 coulomb. That means 40 times 26 times 60. This amount of charge will give how much of volume? That should be multiplied with the amount of like volume we got from one charge. So 4 times 96500 times 40 into 26 into 60. That should give us a volume of 3.9 dm cube. That's how we do it. And if the same thing was asked for, let's say, so, like other solutions as well as molten, don't get confused because molten is very simple. Molten in molten state, whatever ions are given, those will be just simply like participating in the electrolysis. There will be no extra ions. Just in solution, you need to consider if there is the concentrated part for uh, chloride, bromide, and iodide. We only need to consider the concentration, and if not, then the rest like works as per the discharge series or electrolysis reactivity series. Now, we already have heard about the Avogadro constant, Avogadro number, Avogadro constant or Avogadro number. So what does that mean? In equation term, we can say that it is the number of charge in 1 mole electron divided by the charge on 1 electron. Okay, so actually this should be number of charge. This should be charge in 1 mole of electron divided by the charge on 1 electron. So let's say if Avogadro number is L and charge of 1 mole of electron, we already have seen what F. We represent it by F farad divided by E electron. Yeah. Now, just for the estimation, like how would it be? We know Avogadro constant for like assumption we use 6.02 into 10 to the power 23, isn't it? Now, if 1 mole of farad is how much? We just saw 96500. Don't use this in the equation directly because you will be using experiments or this electrolysis process to find this Avogadro constant. So let's say 96500 is the total number of charge, and the electron charge is the charge like the charge of one electron is 1.6 into 10 to the power negative 19. Now, if we place this in the equation, 96500 divided by 1.6 into 10 to the power minus 19, we get 6.031 into 10 to the power 23. So we are almost close. 6.02 and 6.03, like we are almost close. So yeah, that makes like sense that what they're talking about. Now we will be using an experiment to find out this Avogadro constant. So we'll be using actually CuSO4 aqueous with the electrodes being made from copper. Now, one thing I forgot to mention, electrodes, the material for making those electrodes, those rod could be of several types. One is graphite, which is known as inert electrode. Now, inert means unreactive. We already heard about inert gases, isn't it? The noble gases are known as the inert gases. Noble gases are who? Like, who are the noble gases? The group 8 or group 0, group 8 are also known as group 0 elements are known as the noble gases, inert elements, which does not react because they're stable. Graphite is also an inert element. It's not a gas, but it's an inert electrode which does not participate in the like reaction, which does not change its like state or any like characteristic. But there are other electrodes such as copper or let's say platinum. Platinum and graphites are both inert electrode, but platinum is too expensive, so graphite like works for that. Now copper, this is an active electrode. Why active? The name suggests like it actively participate in the electrolysis. So we will see that with time, one of the electrode will get thinner and thinner because they get corroded away. Why? Because the copper of the electrode is actually participating in the electrolysis, hence reducing the size of the electrode. And the other side, other side of the electrode, that will get heavier because more copper is going to get like attached or discharged on the other electrode. But in case of graphite, since it does not form ion, rather it helps to transfer electricity with the electron present, the free electron, delocalized electron present in graphite. Now coming back to our question, we will be using copper electrodes. So Experimental data is given, let's say, the mass of anode at the start, mass of anode initially at the start is, let's say, 56.53 gram, and final mass or at the end is 56.40 gram. Now, what do we instantly observe? The mass actually decreases, isn't it? So obviously that means that like this concept is actually working. From anode, the copper is actually discharging. Like it is actually, let's say, the Cu, it's losing electron in order to form ion and like going like which actually goes into the solution, thus reducing the size of or the mass of the anode. For this like reduction, this actually occurred due to the appliance of 0.2 ampere of current for a time period of 34 minutes, which if we convert into seconds, it will be 34 into 60, which is this much of second. So our solution will be the difference or deposition of Tu equals to 56.53 minus 56.540. Why I say deposition? Deposition means settling down, isn't it? That means the copper, which is being, let's say, like reduction is gain of electron, oxidation is loss of electron, and here we are losing electron. So the copper, which is actually losing electron, here is on the other side gaining electron. Now, how this works? That's what is the main thing of this, like copper electrode. Let's say if we are using copper solution, at this and if the electrodes are copper, then copper actually discharges from this anode. Yeah, reduction like oxidation happens. Copper from Cu2 plus. Now in the solution there is like numerous like thousands millions of copper Cu2 plus atoms. So this anyone from this Cu2 plus atom gets discharged to this cathode, forming Cu, so like Cu metal. So in this Cu metal, we can see, like if that Cu forms, we can see metals being like clinging to the side of the walls of the electrode. That means it is depositing on the sides of the electrode on the cathode. So that's what we are considering, like with the information from anode, that if this much of like that copper is like actually we are getting rid of from anode, that means approximately same amount we will be actually getting on the cathode. Now notice this term I said approximately. That means there are some issues which will be like dealing with just in a short while. But for now, remember I've said approximation. We will work with it later. Now the difference was what? Difference was 0.13 gram. Now this much of copper actually deposited or we got rid of with the presence of like how much of charge? Q equals to IT, which gives us 0.2 into 34 into 60, which is 408 coulomb. Now, if we do the calculation, we would get before doing the calculation, we need to actually write the equation. I'm sorry, I like tend to forget things. So copper plus like this is actually what it is in the deposition part, like where copper is being deposited. What happens? The This is actually known as the cathode. So in cathode, as we are talking about deposition, so Cu plus 2e minus where Cu2 plus gain electron, Cu2 plus gains electrons to form Cu solid. Or on the other side, if we before writing cathode reaction, let's do the anode part. In anode, what happens? Copper losing 2 electron, forming Cu2 plus. Now this Cu2 plus which we just lost is how much? 0.13 gram, isn't it? Has been deposited and the charge being provided is how much? 408. So 408 of coulomb. Now we can say 0.13 gram gives rise to 408 coulomb, isn't it? That much of coulomb is being like used up due to the loss of 0.13 gram. Now, 1 mole of copper's mass is what? It is, if we try to, 1 mole of copper's mass, we often get confused. 1 mole of copper. Now, where will we find 1 mole of copper? Remember, 1 mole means the MR or AR, the value we found, like we usually find in the periodic table. So MR actually means the value given in the periodic table, that is actually the value for 1 mole of mass. So 1 mole of that compound mass. Here, if we find the periodic table, it is 63.45. So we need to find 63.5 gram gives rise to how many moles, how many coulomb, how many charge. It should be, okay, before that we need to find, like using the unitary method, we need to find for 1 gram how many charge should we get. 408 divided by 0.13. That means for 63.5 gram, how much should we get? We should get 408 divided by 0.13 times 63.5. This should be equivalent to 199,292.3 coulomb. Now, how much, like for how many mole of electron is this coulomb? This 408 was for how many mole? 2 mole of electron. That means this is also for 2 mole of electron, isn't it? If 2e minus is equivalent to it, we are just getting 99292.3. Remember, this is not 2 electron, this is rather 2 mole of electron. So rather we can say 2 mole of electron. Then 1 mole of E minus is how much? 199,292.3 divided by 2, which is equivalent to 99646.515 coulomb. Now, if we use the formula where the Avogadro number Na, number of Avogadro or Avogadro number equals to the 1 mole E minus charge divided by 1 E minus charge. Now 1 E minus 1 electron charge is going to remain constant. We don't need to find that. That will be like what we know from the periodic, like from the data booklet, which is 1.6 into 10 to the power minus 9. And for 1 mole of electron, we just found, which is 99646.15 divided by 1.6 into 10 to the power minus 9. This should be 10 to the power minus 19. This should be equivalent to 6.23 into 10 to the power 23, which is like roughly equivalent, isn't it? That was 6.02 here, 6.23. Obviously, we, like as I mentioned earlier, we are actually approximating something, isn't it? This approximation actually more or less gave this error, but this is fine. This is completely fine. This will be your answer. Now, same will be going for sulfuric acid and other cases. If let's say if the electrolysis is being conducted without copper electrode, then what will be the situation? If without copper electrode, that means only the solution's copper will be discharged. Now, in one of the equation, like in one of the example, let's say another example, let's say we have been given from here, let's say Cu against USFR, let's say. Now also we're using copper electrodes. But this time, let's say they have given us the mass for cathode. Now how we do it? How we deal with it? Initially, it is 52.243. Now try to guess, is the mass going to increase or decrease? Before it was anode, the mass decreased. So in cathode, the copper deposits, that means the mass is going to increase. So it's actually that 552.542. See, the mass actually increased. So the difference is actually 52.542 minus 52.243. That is equivalent to 0.299 gram. So del M or del mass, delta mass means change in mass, 0.299 gram. And they're giving us a current of 0.5 ampere for a time of 30 minutes. So Q will be Q equals to IT. That will be very easy to find. 0.5 into 30 into 60 equals to 900 coulomb. Now if you write the equation, now this time the equation should be of what? Of the cathode. Now cathode means copper 2 plus ion being pulled towards itself. Cu2 plus plus 2e minus equals to Cu. Now you might be questioning me that why didn't we use the anode reaction here, and why, like as we know in anode we tend to gain electron. Yes, obviously we tend to discharge anion. We tend to discharge anion by losing electron. But why didn't we like discharge any anion here? Because the electrode was itself copper, and copper is, as I've like mentioned, it's a very active electrode. That means it participates in the electrolysis. It is very like it's highly reactive. Whenever you like apply electricity, it's going to like discharge itself. So it doesn't give the chance for the solution, the like for the ion, for like ion of the solution. Let's say if there was OH minus in the solution, it does not give hydroxide the chance to discharge, so it discharges itself. Okay, so I hope that answers the question. Now over here, like gaining 2 electron, this is formed. The change in mass of copper is how much? We got 0.299 from a charge, like from a total charge of 900 coulomb. Remember, this total charge of 900 coulomb is of 2 mole of electron. If that's the case, then for one, like let's say for 1 mole of copper, how much charge is required? Now, 1 mole of copper means how much of mass? 63.5 gram of copper, isn't it? 1 mole of copper's mass is 63.5 gram. So in order to produce 63.5 gram of copper, how much of charge is required? That's what we need to find. So 0.299 G gives 900 coulomb of charge. That means 1 gram will cause 900 divided by 0.299 charge to be flown. That means 63.5 gram of copper will cause 0.29, like 900 divided by 0.299 into 63.5 gram, this much of charge, which is equivalent to, let's say, 900 into 63.5 divided by 0.299. That is equivalent to 191137.1237. Okay, this is the amount of charge. Now this was actually for how much? How many electrons? 2 mole of electron. This is 191137.1237. That means for 1 mole of electron, that is divided by 2, which will give us 95 points 5, sorry, 95,568.56187. And if this is 1 mole of electron, then number of Avogadro number is 95,568.56187 divided by our charge for 1 electron is 1.6 into 10 to the power negative 19. That is equivalent to 5.97 into 10 to the power 26. See, we are sort of getting a error, but this error is very negligible. Obviously, all the electrons now in this case are not actually depositing to the cathode. Remember, as I mentioned, the approximation term. Now let me say what actually happens when we actually provide electricity. Let's say all of these masses actually get deposited. Okay, like sorry, not actually all get deposited. All of the mass from like this copper, they are like made into like ion, and they went to the solution. From there, not all of them get deposited to copper, less, but a bit less amount goes to the like equation, like deposits to the electrode here, while some are getting discharged, but some of the copper which get discharged just settles down. They cannot stick there. Like let's say they don't get, like if let's say you're in a very crowded place and you're trying to get to the bus, like the bus door is like very like there is packed, like a lot of people are trying to get inside. Or let's say for train, a lot of people is trying to get inside through the like train door. They're very narrow, but let's say crowd is, let's say, 1,000 people. If they all are trying to get into the train one at all at once, obviously few people will left behind because all won't be able to get through it. By the time the train passes, few will be left behind. So that's the thing. It might have like it. Let's say the CO2 plus ion gained our electron, like gained two electron, but it didn't get the chance to stick onto the cathode. So rather, it fall down and settle or sedimented to the bottom. We will obviously see, like in the experiment, some pink solid being deposited to the like, basement. Right, pink solid is due to the formation of copper metal. So that basically it. That's one of the way we could solve it. Another way is if we do like a second method. The second method would be at first finding the mole. So mole is what? 0.299. Well, mole equals to what? Mole equals to mass by mr. So this is the mass, change in mass, and the mr is what? 63.5. That gives us a value of 4.7087 into 10 to the minus 3. That is the number of moles. Now that means copper is 2 electron. We from the equation get the molar ratio is 1 is to 2. That means the value for like the mole for A minus is how much should it be? Half of this one. Sorry, double of this one. Double of this one is 2 into 4.70. Sorry, 4.7088 in 87 actually. 87 into 10 to the power minus 3 equals to 9.42 into 10 to the power minus 3. That's the case. Then we also need to find the charge which we can find by using the formula Q equals to IT equals to 900 coulomb. Now, what is the total number of electrons? Number of Total number of electrons is the total mole of electron, isn't it here? The total mole of electron. Before using total mole of electron, we can use simply the charge. So this is the total charge, 900 coulomb, and charge for one electron is 1.6 into 10 to the power minus 19. So there is the number of total electron, like sorry, the number of total charge for all the electrons. Okay, the all the electrons present, the total number of charge, and the number of charge, like the charge for one electron. So if we divide them, we will get the total number of electron present, 5.625 into 10 to the power 21. That's the total number of electron. If that's the case, this is the total number of electron, and this is the mole of electron. So in 9.47, 9.42 minus 3, this much of mole of electron has 5.625 number of electron. In this much of mole of electron, we get this much, like this number of electron. Then that means in 1 mole of electron, how many electrons, how many number of electrons we will get? That's 5.625 into 10 to the power 21 divided by 9.42 into 10 to the power minus 3 to give us 5.97 into 10 to the power 23. So see, we get the same answer. So anyone you can use. You can use the previous method as well as this method. Anyone would work, whichever you feel like the easiest. In our next lecture, we will see the standard electrode potential. We will learn about standard electrode potential. Standard electrode potential. So that's for today. Take care.